So this work is done with Hanya Zhou, who is my student at Stony Brook University, and Cassandra Hazelman, who is there, and she presented yesterday. But before I start, I would like to thank again Antonia for bringing us together in this wonderful workshop, which I have attended everyone since, so it's the sixth time I'm here. And so this is a presentation more or less related to hardcore machine learning, so that we see what is really under the hood with a specific method that is called flow matching. So what is the idea? I will not have many equations. You'll see more pictures, and I hope I'll be able to convey the main rationale for using this particular approach. So traditional classifiers trying to find this, also known as discriminative methods, to find this probability of a class C given, say, CTG signal, combined maybe with US signals, or maybe other data. Instead, the approach here is to, in fact, find the opposite, to find a distribution of CTG samples given a certain class. And when you look at CTG signals, in particular a segment of, say, 10 minutes, that's typically 2,400 samples. It's a complex distribution. It's not easy to model it. But since the first SPAM workshop, machine learning has advanced so much, and in the past few years, one particular direction of machine learning that has gained a lot of attention is known as diffusion-based methods. So the idea here is again to model this distribution of CTG samples given a class, and then once we have this P of X given C, then we can combine it with the a priori probability of a class, and then we can directly apply Bayes' rule. So in all of my work, I am by religion Bayesian, and not radical, but I do employ Bayesian theory. And the reason for this is because I want all the results that are produced by the methods I apply are probabilistic. So not only that we say this is what the method says about the class, but also what is your confidence in your claim. So the main question again is how to accurately find this object here, P of X given C. So it really, when you look at these methods, they almost work like magic. Let me focus on this particular slide and explain what I mean by magic. So we want to model this distribution of a CTG signal. So what we start with is a segment of, again, 2,400 samples, which are randomly drawn from a Gaussian distribution. Gaussian distribution is very simple to generate. So they represent basically white noise. So this is at one end. We start with this white noise. On the other end is our CTG signal. So we want to now move this distribution slowly from white noise to our CTG signal. We do it slowly. And for this, we use a neural network. So we start with a Gaussian distribution, and then the way how the method works is it has to learn the transformation, how to transform this white noise in something that represents a CTG signal. So again, rather than modeling the final distribution directly, we want to kind of use the principle of divide and conquer. Let's do it slowly, like slow cooking rather than fast cooking. So the main idea is to learn the continuous transformation that transports the original Gaussian to the CTG distribution. And as I said, in the particular examples that I will provide at the end, these will be distributions, joint distribution of samples of vectors that are rather long, 2,400. So we start with a Gaussian. we use the concept of probability flow, and we get the FHR distribution. So this slide shows pictorially what we are actually trying to do. Imagine that on the left side you see a cloud of points. A cloud of points. Each point actually is a vector of 2,400 samples. So you start at quote-unquote time 0, and then you go up to time instant t equal to 1. You do it in steps. And then you pick your point in the cloud, and you start moving it to the right, and then you end up with a sequence that represents a fetal heart rate segment. So in training, we are given a number of such segments, and then during training, the neural network learns how to actually go from left to right. So here you can see at the bottom, we have n tracings, and then at t equal to 0, they represent white noise, and then as you move from left to right, you get a cleaner and cleaner picture of something that would represent fetal heart rate. So basically, in training, we are given these sequences, and then we start with something random, and the machine learns how to go from left to right. So that's beautiful. So why is it beautiful? Then you can now think of, once you finish with training, you can generate a new white noise sequence, and the machine will give you a new CTG signal that is fictitious, but that looks like a real CTG signal that no obstetrician can recognize as being unreal. Like you've seen these AI images of people that are generated artificially. So there's you cannot tell this is artificial and this is, sometimes maybe you can, but depending on the machine, usually you cannot say what is what. So again, let me repeat, we start with training, we start with white noise, and we move this sequence of white noise samples to represent a CTG signal. So now, I did not mention one thing. This is supervised training. What that means is we assign to each CTG signal a class. It could be class 1, class 2, class 3. In our example that we only had 2 classes, class 1 and class 3. And the class label is embedded in the process. So the neural network knows that this is a category 1, category 2, or category 3. So now, this was the training part. So let me repeat again. You start with white noise. You can say, I want a CTG signal of class 3. Boom. You get a CTG signal of class 3, which is new, never measured before. I want a signal of class 2, same thing. Class 1, same thing. So now you can ask a question, so how do we do actually testing? Now we have a new CTG signal, and then I want the machine to tell me what class this signal belongs to. So now you actually go backwards. You start with what you know. You don't know the class. So here is an example here. So what you do is you put the signal through these 3 different channels. So you say, tell me what is the probability that this CTG signal belongs to class 1? And it will produce, you start with this here. I don't know if you can see my cursor. Yes. And then you obtain something that looks like white noise. But if this was not really class say 1, this distribution would be poor Gaussian distribution. So, or maybe very good Gaussian distribution, so it has high likelihood, 0.72 here. And then if, when you put it through channel 2, it will give you a different number, 0.21, channel 3, lowest number. So now this is the likelihood. Now you can employ also your prior, and then using the prior and this likelihood, you can finally obtain your posterior probabilities of the observed CTG. So here's again a pictorial description of what is happening. So we have, when we do training, you see, given the class, you go from left to right. This is like one channel, another channel, third channel. And then when we do testing, we do the opposite. So the beauty of this approach is that you use the same machinery in both directions. And I have here a nice analogy with GPS. So if you want to go from A to B, you ask GPS which way to go, and it tells you how to go from A to B. But if you're in B, you ask again, how do I go from B to A? And it uses the same algorithm. Nothing is really changed. So it is the same neural network, and it works in both ways. There's mathematics behind it. I will not go through it. But these methods, I repeat, for those of you who are in the audience and who do machine learning for a living, I would strongly recommend that you start, if you haven't done already, to start working with diffusion-based methods. So here are some examples. This is very, very preliminary. So we asked Cassandra to label for us segments. We wanted to start with something simple that will not create any controversies. So we didn't have any segments. These are segments of the same length. You can see how they were split. So we had total of 200, and you can see how they were split into training and testing. So it's a highly imbalanced classification problem. I have some comments to make about that also later. And then this is what we got. Actually, there was one mistake that was made where category 3 was classified as category 1. So in conclusion, so flow matching, this is a methodology based on flow matching, it learns continuous probability transport. It transports complete distribution from one starting distribution. During training, it's a Gaussian distribution to the FHR distribution. So the learn flow defines the likelihood model, which so this allows us to compute the likelihood of when we do testing of CTG to belong to one of the classes. So we still use Bayes' rule. We don't have likelihood optimization, and we have some initial promising results. So obviously future work should be much more comprehensive. We would like to work on much more data, to have more categories, and to work with also out of distribution detection. So maybe I can answer some of, I can actually share with you some ideas after I get questions, and then maybe some of the questions will force me to actually share these ideas.
Thank you very much. Right, questions.
This reminds me of when I was doing many years ago. Should I have one model for all the classes or separate models for each class? It's maybe the next step is to bake in the class as a conditioning factor for the generation. Do you only have one neural network?
So again, let me explain how it works. So you have actually a joint distribution of the samples and the class. So if you have three classes, that will be obviously something that the neural network will be trained to do. So I mentioned at the end, now this is one of the things out of distribution. So let us say that you train your network only on three classes. Then when you run your testing example, what we want to develop is that it's called open world recognition. We want to be able to say this particular segment doesn't belong to any of these three classes. It's a new class. So this is the intention of the future work. So to answer your question, every segment has associated class. It's a joint distribution of the samples and the label being the class. And the neural network learns actually how to recognize, again, the class because it is embedded during learning in the network.
Okay.
Yes, thank you very much, Peter. I was curious about signal loss, in fact, because you mentioned you had 240 samples, you're feeding...
Sorry, can you repeat?
I was curious about signal loss, because you have 240 samples you're feeding in and then going also backwards. Assume you have actually 240 samples, but in fact in the CTG trace, often you have samples which are not present. Do you take that into account in your modeling, or how do you deal with that?
So, sorry, for some reason I don't hear you very well. So
a few of your samples, usually in a CTG trace, they are missing because you cannot really measure it for whatever reason, bad quality, and then you have gaps in your trace. And in your approach, you assume you have your 240 samples available, and then going back and forth makes sense, but how do you deal with that?
Yes, so this is important, thank you. So obviously, as you know, when we work with CTG signals, often we have missing samples, and so here you can do one of two things. One can try to, depending on how big the gaps are, you can try to again generate separately, or before you enter your signal to this machine learning to the neural network. You can try to interpolate signals, which you have to be now careful about, in particular when it comes down to interpretation. But a better solution, in my opinion, is to actually let the machine itself the neural network populate the missing samples. But then what is also very important is in making the decision, because now we have samples that are not really measured samples, it is very important to instill in the final result the uncertainty about the missing part of the signal, so that you cannot be so sure about the made classification. So the short answer is that, again, our objective is to have this neural network because it's capable, it can generate samples that are missing, but then the question is, how do we quantify this uncertainty? How does it project on the final result?
Right. Okay. Rolf.
Thank you for this very interesting talk. So you're focusing on the amplitude distributions of the signal, but you're ignoring any temporal behavior. Is that an issue, do you think?
No, I should have mentioned this. So basically it's a joint distribution where actually the temporal part also plays a role. So the neural network knows that the first sample is first in time, second in time, and you cannot interchange the samples. So there's the temporal part is embedded in the modeling. That's very important, actually. Ivan, there's one question there. One question.
I was going to ask you, but okay.
No. First.
Really exciting work. Thank you. I was wondering two things. One is, if I understood correctly, you have the same dimensionality as you do your flow matching. So you are maintaining the dimensionality as you start from the Gaussian from the Gaussian distribution to the distribution of the fetal heart rate. I was wondering if we could do some compression and then go towards the CTG trace, because maybe that can also help with some amount of denoising because we are compressing. Second question is, we have also been seeing that longer term knowledge can also help with classification. So so does your method also handle variable input? Because, yeah, important to see that as the fetal response evolves, we want to understand if it's starting to deviate. So can this method also incorporate these aspects?
Yeah. So this is another excellent question, because I can now comment on what I had in mind to say for future work. So first, here in this particular, with this particular approach, we don't do any compression. So basically, whatever you have at the beginning, if it's 10,000 samples, 10,000 samples. The second question is, what we had done here was independent classification. But as was mentioned, when we do monitoring, we want to know what happened before that. And so we have some ideas how to actually now use this additional information so that we know what happened in the previous, with the previous time segment. And of course, we can also overlap these segments, and so there are plenty of interesting directions for research. So yes, the idea is, so several ideas. To do it in time context. Second idea is to allow for out of distribution, so to have the machine to learn on its own. But then I also would like to, what to me is really the most challenging and the most beautiful question is something that was mentioned earlier, how do we unlearn? So I don't want to rely on Cassandra all the time. So, so how do we do it in an unsupervised way? And then I remember when we started to work together, Cassandra will tell me, no, I want you to teach me how to interpret CTGs in a different way, not that we teach the machine how to do it according to humans.
Okay, last question. So it sounds to me, Peter, you're doing a magic. You pick up a cloud of points,
yes,
and you transform them into CTG section or sector or whatever. And then you go backwards to test, similarly to backpropagation. Now, to convert your point or cloud to a specific sequence of points in the CTG, you need a measure of the discrepancy, the network that will try to eventually reduce it. In other words, an error function for this. So how exactly, what do you apply there?
So the way how it works is, yes, it sounds like magic. So one, actually, for someone like you, when we teach probability theory, one of the important classes in the subjects in a course in probability theory is transformation of random variables. How you go from random variable x to a random variable y, or from a random vector x to a random vector y. And we know exactly how to do it. It works in the same way, by transformation of random variables.
Okay, thank you. So we will move to the next presenter. Julia is here. Thank you very much again.